Entropy, which is symbolized by a capital S, is disorder. Processes in which the system's disorder or the system's entropy increases tend to occur spontaneously. There are actually a couple of terms that give you the feel for what entropy is. Disorder is one, chaos, randomness. Those are all terms that describe entropy. The change in entropy of a process, obviously, is going to be the final entropy minus the initial entropy. If the sign of the entropy change is positive, that means that the final state has more disorder than the initial state. More chaos, more randomness. Processes that have a negative change in entropy means, again, look at the equation. If this term on the right ends up being negative, then mustn't the initial chaos be larger? There must be more chaos initially than at the end. Products are more ordered than reactants. Large or high entropy means lots of chaos, lots of randomness, lots of disorder, or sometimes it's called it has a large number of microstates, a large number of possibilities for how things could be. Here are two pictures of high entropy. There's a lot of chaos, there's a lot of disorder. Small entropy, or low entropy, is less disordered. And if we look at these pictures, we can see there is less chaos, there is less randomness to these pictures. And now we can compare one room which has high entropy and another room which has low entropy. So, entropy is the amount of disorder, the amount of randomness, of chaos. There are three types of motion, each having kinetic energy. And here they are: translational, vibrational, and rotational. Translational motion is here to there motion, as this dude in the bow tie just demonstrated. He moved from the lower left to the upper right. That is translational motion. He's now going to demonstrate vibrational motion, and there he is, just wiggling back and forth, and now rotational motion. Now, the motion of a given particle isn't confined to necessarily just one of these. Our friend is now going to demonstrate all three of these at once. He was rotating, he was vibrating, and he was translating all at the same time. The more kinetic energy something has, the more entropy it has. The faster things are moving, the more chaos there is, or the more microstates are possible. So in general, as the temperature increases, so does disorder, so does the entropy. As the temperature decreases, so does the disorder, so does the entropy. And, in general, which state of matter would have the most entropy? Or, which state of matter would have the least? Well, solids are more orderly. Their particles are fixed in place, just vibrating. Gases, the particles are moving in random directions, so there's definitely a lot more chaos in a gas, and there's the least amount of chaos in a solid. How about these phase changes? What would the sign of the entropy change be for freezing, melting, condensing, and boiling? Well, let's consider freezing first. In freezing, we're starting at a liquid and we're changing into a solid. We are going from particles that can slide relative to each other to a state where the particles are fixed in place and just vibrating. Whenever we do change, we go final minus initial. So the final chaos in freezing is a smaller number. The initial chaos is higher. Smaller chaos minus greater chaos is going to give us a negative number. Melting, of course, is the opposite of freezing. And so let's think, when we melt, we start out as a solid. We end up as a liquid. The final entropy is higher. The initial entropy, the initial chaos, is lower. Final minus initial will, of course, give us a positive number. How about condensation? When something condenses, when a gas condenses, does the amount of disorder increase or does it decrease? it definitely decreases, because we started out as a gas, which is very chaotic, and we ended up as a liquid, which is less so. And when we boil something, does the amount of disorder, the amount of chaos, the amount of randomness increase or decrease in the boiling process? It definitely increases. Entropy increases when the number of gas particles increases. In this example here, you can see we're starting with 2 gas particles, and we end up with 4. There are any number of ways we could describe this. We could say that on the right there are fewer bonds. Actually, feel free to count them. On the reactant side, we have a total of 6 bonds, and on the product side, we have a total of 4. So there are fewer bonds, there are fewer restrictions on the motion of atoms, there are more degrees of freedom, there are more possible microstates. There are any number of ways that we could express the same thing. In all cases, what it boils down to is that the entropy increases. Similarly, when liquids or solutions are formed from solids, solids have relatively low entropy. A liquid or a solution would have a higher entropy. And when gases are formed from liquids or solids, gases have higher entropy, liquids or solids have lower. Let's pick and choose here. Which has the greater entropy? 1 mole of oxygen at 300 Kelvin or 1 mole of oxygen at 500 Kelvin. Let's say they're in the same volume. Clearly, the one at the higher temperature is going to have more chaos, more disorder, more randomness. How about the next one? 1 mole of KCl, which is a solid, at 300 Kelvin, or 1 mole of HCl gas at the same temperature. Well, here, the gas will definitely have more chaos, more entropy. How about the next one? 2 moles of HCl gas at 300 Kelvin, or 4 moles of HCl gas at 300 Kelvin. 4 moles of gas has more entropy than 2 moles of gas. There are more possible configurations for 4 moles of gas than 2. More possible microstates. 1 mole of HCl gas at 300 Kelvin versus 1 mole of argon gas at 300 Kelvin. This is kind of a tough one. We have the same volume, we have the same temperature. How would we know which one is more random, more chaotic? Well, the answer here is going to be the HCl, because an HCl, if we look at it the way it's written, there's an H on the left and there's a Cl on the right. If we flip it, imagine flipping that molecule where the Cl is on the left and the H is on the right. It's the same molecule, but that's a different microstate. Or we could rotate that molecule so that the H is on top and the Cl is on the bottom from our perspective. That's a different microstate. Now, look at the argon atom. If you take an argon atom and you flip it left and right, or you flip it up and down, it's exactly identical in either of those orientations compared to what it was. So there are fewer possible microstates for the argon. How about the last one? 2 moles of HCl gas at 300 Kelvin in a 10-liter vessel versus 2 moles of HCl gas at the same temperature in a 5-liter vessel. The one where there's more space has more possible microstates, more possibilities for how particles could be arranged.